很荣幸今天能给大家介绍我们最近关于latent diffusion 的一些它的缩放以及蒸馏特性的工作的研究。这个研究的目的是为了找到关于 latent diffusion model 的它的 scaling law 以及如何才能有效的利用 latent diffusion model 在高效并且高质量的图像生成任务当中。我们这个工作的背景是关于 diffusion model。diffusion model 它可以看成在利用一个去噪网络，通过在噪声图像当中去噪，然后得到清晰图像的这么一个过程。从噪声到清晰图像其实是一个在两个 distribution 上面的一个变化的过程。然后我们可以从一个 empirical 的标准高斯噪声分布，把它利用这个去噪模型，通过 progressive 的去噪，然后把它映射到一个自然图像的 distribution 上面。它的去噪模型一般是采用 Unet 作为网络的 backbone， 并且为了减少计算量，我们一般会把图像通过一个额外的 encoder 和 decoder， 把图像做下采样来缩放这个特征空间。所以在这个基础上，比较流行的diffusion 网络叫做 latent diffusion model， 是或者大家比较熟悉的 stable diffusion， 就是基于这么一个 framework 的设计，然后通过这么一个在特征空间上的去噪网络来实现图像生成。Diffusion model is very popular, but it's less popular than large language models. That's because in large language models, we have a scaling law. This scaling law, it reveals the ruler between the model size and the computer and also the training data. It says as long as you have enough training data, you can determine how large the language model you need and according to how many computer you want. And you can also estimate how is the model's performance even without training the model. However, we don't have such thing in diffusion models. So in this research, we are interested in what's the scaling law of a diffusion model, how should we design a diffusion model according to the training computer that we want, and also is there anything special for diffusion models that we don't see in large language model. Because as we know, the difference between diffusion model and the language model is that you can get much better results by using more iteration steps, that is using more inference computer. So we're interested in how this inference computer variant affect the fellow performance of a diffusion model. In order to conduct research, we choose one of the most popular generative model, that is stable diffusion. We know the stable diffusion is a middle-sized model. It has 800 million parameters, but it can generate very high-quality images according to text prompt. So we're interested in what if we scale down the stable diffusion, and what if we scale up the stable diffusion? How is their performance? Can we get a similar law according to the transformer used in large language models? So in particular, we try to scale up the model into 5 billion. That is more than 5 times more parameters than the original one. And we also scale the model down into 39 minutes. That is close to 1 over 20 model sizes. And by training those models from scratch, we indeed see very similar properties as the large language models. That is, as long as you have more training computer, you can always get more performance by increasing the model size. And this performance is also is reflected on both the FID performance and also the clip performance. However, besides this expected scaling law, we indeed see the other thing that is more interesting. We also have the other findings. Based on this text-to-image scanning experiments, we also find that if we fine-tune those text-to-image scaled model and on the downstream task like text-to-image, we also find that even though you can put more computer on small models, the small models performance cannot outperform a large model. Even the large model is using less computer. So we conclude that the downstream performance of a diffusion model is actually depends on its pre-training performance. So it means the text image pre-training, it actually scales the downstream performance. We can also see it from the visualization of a super resolution. You can always find that the large model can always outperform the small models. And we also conduct experiments on the dream boost task, because dream boost is actually less depends on the downstream fine-tuning, but you can still see that the group of small model still cannot outperform the group of large model in facial qualities. And those are about the training law, but we also find the other more interesting thing that about the inference law. So let's say we first define what's the inference of diffusion models, because we know in transformer is autoregressive generation. The cost of its inference is actually less depends on the other factor except the very recent like using chain of thought. But in diffusion model it has its own chain of thought. That means as long as you can put more inference step doing the sampling process of diffusion, you can always get better performance. So first we try to define what's the inference compute of diffusion models. So we first unify the diffusion model by calculate their sampling cost as the sampling steps times the g-flops of each sampling step. So it allows us to compare the inference computer of the diffusion models. Like for example, we can say for the same 150 steps, you can always see the larger model use more sampling cost, and at the same time, if we say we only want the same sampling cost, we can see at the same sampling cost, small models can use more sampling steps, the larger models can only use small sampling steps. Based on this 5 sampling cost, so we then compare how is the model performance when they are using the same sampling cost. For example, here let's say, what if we only have 10 sampling costs? How is the model's performance? And we found some very interesting observation that is under the same sampling cost. The small diffusion model, for example, like this green one, it actually can achieve the better performance like in terms of FID than the large diffusion models. And even the large diffusion models use more computer, its performance is still inferior than the small diffusion model. And we'll also do the visualization to see whether this is true or not. As you can see in like 6 sampling cost, you can always find a smaller diffusion model that is generate much better facial quality results than large models in text to image. And even increase your sampling budget, you can always see you can always find a smaller diffusion model that can outperform the large diffusion models. So this is one of the most interesting findings in our scaling experiments. It refutes any inference scaling law of a generative model. That is, it tells us instead of simply scale up your generative model, you can try to scale the inference. And one day, once your generative model reaches the boundary of scaling up, the other path you can choose is the scaling inference. And this is also another example. And we also found some very interesting thing that is first, even we also find that this scaling law is irrelevant with the other factors, like you can use a high order sampler or use a stochastic sampler, but using different sampler usually will affect the behavior of diffusion models. Like if you use a stochastic sampler, you will get a worse performance when using less step, and use the high order sampler like DPM solver plus, you will get better performance in small sampling steps. But still, you can also find a similar scaling law of diffusion models. Another very important aspect about the diffusion is that using more sample steps can get better performance, but also slows down the inference time. So nowadays, people start to try to reduce the sampling steps without hurting the performance. That is the destination. But how does the destination affect the inference scaling law of diffusion models? So in order to understand this, we also in our other recent work, we also tries to propose a new destination method. So in order to understand this destination method, we first need to go deeper into diffusion models. As we mentioned before, diffusion models, it has two processes. The first process, it adds noise to the image that distort the natural image distribution into a standard normal distribution. This process can be seen as a forward SDE. As you can see, this SDE, it depends on the time variant and also the stochastic process to get the fellow normal distribution, and the deloading process is actually the way of reverse this SDE by using a deloading network that is this part. It estimates the score in this SDE process. The first attempt that to distill diffusion model is to design a teacher network and a student network. Here in this example, the student network F theta tries to match the output of the teacher network F eta in multiple steps. But as you know, this is a very difficult process, and this destination is a very difficult task to learn. So later, people try to using a progressive way, that is, instead of using a single student network, we can use a multiple student network, and each student network F theta, it only learns a very few steps of the teacher network F eta. By doing so, the progressive distillation becomes a common way that can use to reduce the sampling steps of diffusion models without hurt the performance. As you can see the results in the right, that is the distilled network, it can achieve a reasonable performance that compared with the normal undistilled diffusion models in 64 steps with 8 steps only. If we put those methods in a view of the deloading process of the diffusion models, that is, in a standard diffusion models, each time when we try to deloading, that is, we are trying to find the direction that moves in this ODE path, and the diffusion destination is trying to use a addition network that tries to predict the score that is more straightforward than the original one that can get into the original distribution. However, this is a very hard method, and in this work, what we are trying to do is that on the original distribution, we are trying to using a new addition network. Like in this research, we are using the controllet. We use controllet as a base that to shift the estimated score at each continuous steps, and the target of this controllet is tries to ensure the score at each step that is always same as close as to previous one. That because once the score is very similar in each time step, that means its direction that has a sudden change, and the OD path will more closer to a straight line. In this example, that what we are trying to do is that use this controllet to reduce the difference of a score in each step. So the diffusion model only needs one single step. Like for example, we only need the diffusion model estimate score at here, but it can also get a very close estimation than the original one. And also, as you can see that this method, it also changes the samples from the original one as a new one. Instead of enforce the network always estimate the original example, will allow our method by trying to allow the sample the estimated sample shift to allow the network to get a more easy learning. Specifically, our method is implemented by using a network adapter on top of a pre-trained deloading network. It's similar to controllet, but instead, this controllet it aims at the destination instead of image transformation. And we call this method, and this method it doesn't essentially needs to take an image as input, and we call this way of a destination as using a narrow ODE solver to help to solve the diffusion models. We validated this method on super resolution. As you can see, compared with the original undistilled method, the network after destination can generate much more high quality results than the original one, and also quantitatively, as you can see that the method after destination is actually can achieve the comparable performance as the original one, even in 50 steps or 250 steps. And this is the large image of a distillation. We also try this method. We also try to distill the instruct peaks to peaks by using this controllet, and we found that in this more easy task, our method in a single step can even achieve the comparable performance on the original one after 200 steps. And this is the impending experiment. So this experiment has fully demonstrated the effectiveness of a destination method, and we're interested in how this destination method can affect the scaling properties. And you can easily see that in the left figure, we compared our distilled method with those antecedent methods performance in terms of model size. As you can see, our method can constantly achieve a stable destination effect. Our destination method in 4 steps performance can constantly achieve comparable performance as the original one in 20 steps. And this is irrelevant with the model size. But however, if we put those distilled 4 steps methods on the original one sampling cost first performance figure, you can see our method still under the certain sampling cost. You can still find a smaller model like this one, 83 million models. It can also achieve comparable performance as another 800 million diffusion models. So it means that if after distillation you can still find a smaller model that achieves comparable performance than the large model, even though the large model is after distillation. And this is the factualization. As you can see, this smaller model its output, the flash quality of its output is still comparable with the large one under the same sampling cost. In summary, 最后我们的总结是，对于潜空间扩散模型，我们总结了6个规律，其中前2个关于模型的训练的缩放定律，我们发现它是完全符合Large Language Model 的缩放定律。然后我们再发现最重要的是，与Large Language 不同的是，特征潜空间缩放特模型的话，它其实是小模型也能取得比大模型更好的效果，通过增加 inference 的计算量。然后关于这点特性，无论是采用不同的采样方法，或者在不同的 downstream 任务上，我们都观察到了同一的特性。我们认为这一点对于设计小的高效的 latent diffusion model 是很有帮助的。最后我们也同时也发现了，目前现有的 distillation 的方法其实也并不能打破这一定律，所以说明这定律它可能与 diffusion 模型本身的背后的特性有关，而不仅仅是模型大小的问题。然后本次 talk 我们主要就是分享了我们的这6点发现。如果大家有更多的疑问，我们欢迎大家在留言区评论，我们也会后续给大家解读。谢谢。